Assalamu alaikum. This is ID 2006087 from Group 6, presenting our project presentation, IoT-based system for real-time monitoring and control of food storage conditions. Here is the outline of our today's presentation. Our system monitors key environmental parameters like temperature, humidity, and gas concentration. Based on these values, it automatically activates misting, cooling, or ventilation. The goal is to reduce spoilage, improve shelf life, and offer a scalable, low-cost solution suitable for local markets or households. Post-harvest losses in Bangladesh are high due to poor storage conditions and lack of automation. Manual monitoring is time-consuming and error-prone. We explored IoT as a solution. Its ability to offer real-time updates and automated responses can greatly reduce losses and improve food safety. Our project specifically targets the problem of fruit spoilage caused by temperature, humidity, and gas buildup. The system we designed can monitor these in real time and take corrective actions automatically, making it ideal for small-scale vendors or home users. We studied existing works like Ansari and Gupta, who used DHT22 Peltier modules and gas sensors in food storage. We were inspired by their successes, but wanted to build a more compact, affordable, and integrated system, combining all three major controls in one box. We chose DHT22 for temperature and humidity and MQ135 for detecting spoilage gases. These sensors feed data to an Arduino, which triggers physical actions like misting or venting based on safe thresholds. This allows 24/7 autonomous monitoring. Our control logic is built into Arduino Mega, supported by relays and servos to control mist, fans, and Peltier cooling modules. The ESP8266 Wi-Fi module allows wireless updates, and the system is scalable and affordable for real-life deployment. This is our system workflow. First, sensors collect data, then the controller checks if any values cross the set limits. If temperature and humidity are high, the Peltier cools the box. If humidity is low, the mist module activates, and if gas levels rise, the fan vents it out. All actions are automated and real-time.
Assalamu alaikum everyone. I am Muhammad Al Hussain, ID 2006090. Here you can see the complete circuit diagram of our IoT-based crop storage and monitoring system. Now I will walk you through how we implemented each part. Here we can see that we have used two key sensors, the MQ135 gas sensor and the DHT22 temperature and humidity sensor, both connected to the Arduino Mega. This provides the essential environmental data for our system. For cooling, we have used a Peltier module. On the hot side, there is a heatsink and fan to remove excess heat. On the cool side, we have placed another heatsink and fan to evenly distribute the cool air inside the storage box. The control system is managed through relays. One channel controls the Peltier module and another channel controls the Peltier fans. We have added another relay module for other components. One channel operates the inlet and outlet fans, while the other controls the mist module, which is responsible for humidifying the storage environment. For power, we use a 12-volt 10 ampere SMPS. It directly powers the Peltier module, Peltier fan, inlet and outlet fan. From the same SMPS, a buck converter steps down the voltage to 5 volt, which powers the relays, sensors, servo, and the ESP8266 Wi-Fi module. This is our hardware implementation. All the components are connected as per the design, ensuring proper operation. Here you can see that the jar inside the storage box, it collects the water droplets formed on the cool side of the Peltier preventing them from dripping directly into the fruits. Now for the results. On Saturday, 26 July at 6:50 p.m., the temperature inside the box was 31 degrees Celsius and humidity was 85.7%. By 11 p.m., we see that the temperature had dropped to 23.6 degrees Celsius and humidity had reduced to 74.6%. Our experiment continued from 26 July to 28 July. By the end, we could clearly see a visible improvement in the fruit's storage inside compared to the started condition. Here is the IoT Cloud dashboard. It is accessed via both mobile and web. It shows real-time readings of temperature, humidity, inlet-outlet fan status, and whether the Peltier module is on or off. And finally, this is our expected prototype design, the model we envision for the finalized system.
Assalamu alaikum. I am MD Muaz Rahman. My student ID is 2006089. Now we will discuss the design analysis and evaluation for our project. This section covers the novelty of our idea, design considerations, investigations and limitations, and how our system aligns with societal, environmental, and ethical goals. These aspects also map to the program outcomes POC to EOH. Our system is novel because it combines multiple environmental control mechanisms like cooling, humidifying, dehumidifying, and gas detections, all in a compact box. It automatically controls the environment using sensor thresholds, which is user independent. We used a Peltier module not for just cooling, but also for dehumidification, which increases efficiency. Ventilation is controlled using servo motors triggered by gas detection from ripening or spoiled fruits. And the design is low cost and compact, making it suitable for domestic use or any small-scale vendors. We addressed three design aspects under POC. First, public health and safety. The system avoids spoiled fruit consumption by maintaining proper storage conditions. Second, environmental consideration. By reducing spoilage, we reduce waste, and the system itself uses low power components. And third, cultural and societal needs. The design supports local food preservation, especially useful in places with high post-harvest loss like rural Bangladesh. To validate our system, we ran several experiments. We tested the MQ135 gas sensor using overripe fruit to confirm that spoilage gases could trigger the system. We monitored temperature and humidity readings to tune the mist and cooling functions, balancing energy and effectiveness. Lastly, we studied how fruits are typically stored in local homes and shops, and we adapted our design to those real-world needs. Every component has its limitations, and we took those into account. The MQ135 sensor requires proper calibration and can vary with humidity and also varies with unit to unit. The DHT22 sensor can be slow and slightly inaccurate. The Peltier module draws a lot of current and takes time to stabilize. Our relays only offer binary control, no speed modulation. The mist module can sometimes over-humidify, and open wiring setups may introduce noise or interference. We assessed the impact of our design on three levels. Culturally and socially, it promotes better preservation of local produce and reduces waste. In terms of health, it reduces the risk of consuming spoiled fruit by detecting ethylene and other gases. Legally, our system operates safely within general electrical guidelines, and there are no data or safety regulation violations. Our system supports sustainable practices. By extending fruit shelf life, it supports local food storage and reduces unnecessary waste. It promotes long-term food safety, helping prevent early spoilage, and our design doesn't conflict with safety or electrical standards, meaning it can be safely deployed and maintained. From an ethical standpoint, we ensured safe electrical design using proper insulation and by isolating high current paths. All components were selected with care using reliable suppliers and safe ratings. Currently, there are no data privacy risks, but we noted that if the system is expanded to use IoT and cloud storage, ethical handling of user data must be ensured. This completes our design evaluation. As you can see, we not only built a working prototype, but also made sure it's practical, safe, and socially relevant.
Hello everyone, this is Mohammad Al-Amin and my student ID is 2006088. I'll cover the final part of our project presentation, the IoT-based system for real-time monitoring and control of food storage condition. Let me begin with our individual contribution. Throughout the project, we ensured task distribution for efficiency. Pushpita and I were responsible for sensor selection and calibration. I also collaborated with Moaj in testing, validation, and documentation. Al Hossein and Moaj worked on the cloud dashboard, while Pushpita and Al Hossein handled coding and integration. The full system wiring and setup was a joint effort among all the members, including myself. Our logbook outlines our weekly progress. We started with topic finalization, moved on the sensor testing, relay integration, and cloud features during the break. Week 8 to 12 are mostly hardware focused, including fan and mist module integration, threshold testing, and complete system assembly. In week 13, we did a full live test with real fruits for 48 hours. Condition remained stable and fruits stayed visibly fresh. Finally, in week 14, we wrapped up the packaging and reporting. To communicate it externally, we uploaded our code base to GitHub and created a demo video on YouTube for broader access. This ensures transparency, allows feedback, and supports replication by others. Now, moving to the project management and cost analysis, we documented every component and cost aspect of the project. We aim to keep the design affordable without compromising on critical features, which shaped all our decisions. Our bill of material includes all the necessary sensors, modules, fans, and structural part. The total cost of our prototype reached around 10,660 BDT, though many items are used in testing and iteration. Each component was chosen based on its functionality, cost effectiveness, and availability in the local market. For a more refined unit, the optimized per unit cost is around 6,500 BDT, which includes only the essential. The version represents the minimum viable product that can still deliver all the key features of our system effectively. When scaling to mass production, assuming 100 units, the cost drops to 4,345 BDT per unit. This makes our design both scalable and market-friendly for small vendors and rural application. We also did a comparative analysis. The MQ135 sensor was chosen over MQ2 or MQ3 due to its ability to detect spoilage gases like ammonia and formaldehyde. Relays are used instead of MOSFET for simpler on-off control. We used a standard icebox as our enclosure, reducing thermal leakage and cost. All the components were sourced locally to ensure affordability and availability. Here is a summary of our implementation timeline from the component selection in week 6 to final testing and documentation by week 13. The clear weekly breakdown helped us manage time, divide tasks, and avoid last-minute rush. For future improvement, we envisioned 4 major upgrades: a mobile app to make real-time monitoring more user-friendly, an AI integration for early spoilage detection and predicted control, a solar-powered setup to support use in off-grid rural areas, expansion into a network system that can monitor multiple storage locations from a central interface. Lastly, we cited all the sources that guided our work. These include recent paper on IoT-based storage systems, sensor integration, and cold chain monitoring. To conclude, this project helped us apply what we have learned in embedded system to solve a real-world problem in food preservation. Successful integration of sensing and Automation and control in a low-cost package gives us confidence that our design can make a practical difference. Thank you for your attention.